Hello, everyone. We are the Moon Exploration and Habitation Team. Our project name is DREAM, which stands for Discovery, Research, Exploration, and Analysis on the Moon. Today, we will present our design concept for a lunar research-based system, which addresses long-term moon habitation and explores research working directly with native lunar materials. But first, I will introduce our team. My name is Yelisey Romanov, and I'm the Radiation and Travel Safety Specialist. Samantha Moorhead is our lunar base architect, and Johnston is our cosmic transit specialist. Judith Martinez is our physical and mental health specialist. Srimann Nambakkam is our data transfer specialist, and Angelina Tran is our landing site specialist. Additionally, Judith, Sam, and I are in charge of the Alpha experiment. Sam and Angie are in charge of the Rim experiment. Judith and I are in charge of the Plant experiment, and Srimann and Anne are in charge of the Lunar experiment. The goal of our project was to create a plan for a permanent moon habitat which supports 4 specific lunar experiments. Additionally, we designed our experiments to be beneficial for further development in space habitat design.
Space radiation is one of the more dangerous hazards of space travel. Typically, space radiation refers to high-energy galactic cosmic rays, solar particle events, and coronal mass ejections. The Earth's atmosphere and magnetic field block cosmic radiation, preventing high-energy gamma waves from reaching us. However, the atmosphere and magnetic field are absent on the Moon. If astronauts fly without proper shielding and countermeasures, they will be exposed to gamma radiation, leading to an increased risk of cancer, neurological disorders, and degenerative tissue defects. Light mass, hydrogen-rich materials should be used to minimize the radiation the crew is exposed to. Previously, NASA utilized polyethylene to protect the ISS from radiation. However, we will be using Kevlar since it is just as effective at shielding radiation as polyethylene, and it can be incorporated into our inflatable lunar habitat. At best, Kevlar might reduce the equivalent radiation dose by 34% at 5 grams per centimeter square thickness. Therefore, radioprotective agents and medical supplements should also be used to ensure the safety of astronauts. Astronauts should consume antioxidant foods such as onions, tomatoes, and carrots to reduce radiation-related oxidative damage. Additionally, pharmaceutical treatments such as radioprotectors and radiomitigators can be given to astronauts exposed to high-energy ionizing radiation, respectively. Finally, scientists can monitor the radiation levels in the habitat using a hybrid electronic radiation assessor and assign treatments accordingly.
Commercial lunar payload services, also known as CLIPS, will be crucial in sending prior necessities, support frameworks, and technologies before the astronauts' arrival to lunar service near the permanently shadowed regions. Examples of these American commercial companies consist of SpaceX, Blue Origin, and various other companies. Together, these companies will help NASA expedite the mission process, mission requirements, and stimulate a new upcoming space economy. According to our plans, the first payload is to be transported 2 weeks prior to the astronauts' arrival to the lunar surface. This payload will consist of our deflated lunar base and our energy source of solar panels within the rocket. The second payload will arrive a week prior to the astronauts' arrival, consisting of the technologies, our lunar terrain vehicle, as well as our ice tracking and lunar regolith collecting rover. Our last launch, which will be a few days before the astronauts' arrival, will consist of the astronauts' food, medication, and resources, which will be used by the astronauts on a nearly regular basis. To achieve the goal of sending our payloads out and our astronauts, the DREAM mission will combine use of both SpaceX's Starship rocket and NASA's Space Launch System. Starship will be our primary method of transporting heavy payloads because of its size, payload capacity, and ability to alleviate costs with its reusable Raptor engines and super heavy booster. NASA's SLS rocket is also a great option because, similar to Starship, its advanced core stage and use of liquid oxygen and hydrogen make it another great resource for transporting payloads and the astronauts. Lastly, Gateway will be crucial in the DREAM mission for communications, transportation, monitoring, and more. It will also be essential in the arrival of the astronauts to the lunar base with its highly elliptical near rectilinear halo orbit and international partners, which will help make the arrival of the astronauts successful and create a path for future Mars missions.
An important aspect of building a lunar base is selecting the optimal landing site. After lots of consideration, the peak near Shackleton crater was selected based upon reviewing the following parameters: sunlight for power, area for landing, permanently shadowed regions, etc. The most important aspect is the existence of water ice, a necessity to human survival on the lunar South Pole. Satellites have confirmed that the albedo, or natural reflection, of the crater is high, thus highly suggesting water ice. Additionally, MIT believes that water ice may make up to 22% of the crater floor's micron-thick layer. Furthermore, 3 points on the rim are continuously lit for 90% of the year, which leads to stable temperatures. Not only that, but the terrain is smooth compared to other regions. With a slope of 5 to 10%, it is a suitable area to not only build a lunar base, but explore. Currently, NASA is reviewing 13 landing sites, and the peak near Shackleton crater is our recommendation. While the landing site is not in the line of sight for direct moon-to-Earth communication, we are excited about demonstrating a capability of routing communications through satellites and space stations such as the Lunar Gateway Space Station. Overall, Shackleton will best take care of our needs for human existence and science experiments by allowing a foundation for both sunlight and opportunities to explore permanently shadowed regions for Artemis missions in the short and long-term project plans for NASA.
The Lunar Lab must be able to withstand a wide variety of threats present on the Moon, such as a lack of atmosphere, radiation, micrometeor showers, launch debris, regolith dust, humidity, and extreme temperatures. Due to the necessity of protecting against micrometeor showers, the base structure needs to evenly distribute forces and pressures. The best structure for this is a geodesic dome, which is a hemispheric structure that utilizes triangles with their geometrical advantages to distribute stress, enabling it to endure heavy loads effectively. This lunar base also has a hybrid inflatable design with 2 layers. The inner layer is an inflatable membrane structure, which is very beneficial for transportation as it is cheaper to travel and takes up less room. The inside layer will be made up of multiple layers made primarily of Kevlar 29, which is resilient to radiation and good for installation. This layer will also serve as the temporary base while the outer base is being built. The outer layer will be made of lunar regolith bricks, which can be developed through a process of crushing, melting, and compressing the regolith to make concrete-like material. By working towards in-situ resource utilization, or ISRU, we limit the materials we must bring, break the resilience of the Moon to the Earth, and help with protection from both micrometeor showers and cosmic radiation. The entrance is in the garage, where we will store all rovers, robots, and be able to repair parts, as lunar surface is extremely abrasive to mechanical and electronic components. Through the airlock, the astronauts will be able to store spacesuits and access the main base, which will house communications and central lab equipment. This is connected to a storage area, which will house environmental control and life support system, a very powerful filter, and other supplies. The living area, also linked to the central lab, serves as the astronauts' dining, sleeping, and workout space, as well as our Alpha Lab. The RIM Lab and in Spacesuit Lab is outside the garage, and both Plant and Lower Region labs have their own lab, with Plant having access to a greenhouse. For all of this base to be powered, we plan on using solar panels. Since we are in the South Pole, solar power is a very feasible option as we receive sunlight 90% of the year. The solar panels will make up 125% of our estimated energy budget, allowing for a margin of error.
During an astronaut's stay on the Moon, they must stay in excellent physical and mental shape. An astronaut's food nutrition, water quality, base lighting, exercise schedule, spacesuit, and sleep schedule are essential to keeping an astronaut mentally and physically fit. One of the biggest issues with the reduced gravity on the Moon is loss of bone and muscle mass by 1% for every month spent in space. To stop reduction of bone and muscle mass, the astronauts must exercise at least 2 hours every day. Besides losing muscle and bone mass, astronauts will experience a disruption in sleep and appetite. The lunar base must have lighting that simulates Earth conditions in order to allow the astronauts to develop healthy sleep rhythms. The change in appetite that might be experienced might be due to the lack of food variety. To solve this, many different types of dehydrated food must be brought up to the Moon. Some examples of food and drinks to take are MREs, freeze-dried food, powdered drinks, dried goods, and canned goods. About 360,000 calories worth of food must be brought to the Moon in order to support 4 astronauts for the 45-day mission. Taking water to the Moon is expensive, so an environment control and life support system, along with 530 gallons of emergency water, will have to be installed in the lunar base. The environment control and life support system recycles all water in the base, whether it be sweat, urine, or wastewater, and turns it into drinkable water. Another big issue on the Moon is lunar dust. Lunar dust, also known as the regolith, adheres to any and practically all fabrics because of its sharp edges. Lunar dust can cause respiratory damage, ocular damage, and much more. An astronaut's spacesuit material must be made from Kevlar, which has thermal stability and high strength, to minimize adherence to regolith. Regolith can't be completely avoided, but measures like the electrodynamic dust shield can be used to lessen exposure to regolith. Regolith can also wear down electronics and machines by jamming them with small particles. For this reason, regolith must be considered when designing spacesuits and machines. In the experiment, Advanced Lunar Physiological and Health Assessments experiment, we're going to be testing radiation dosage, heart rate, bone density, body temperature, blood pressure, urine samples, and blood samples.
We are doing this so that we can help diagnose any potential problems in our base design, which we can address as soon as possible. Our hypothesis for this is if humans live on the moon for 45 days with protective suits and a secure base, then there will be effects on human health, however, it will be minimal.
Regolith's impact on materials, or RIM, will test the impacts of regolith on 3 different types of materials: Kevlar 29, Tyvek, and ultra-high molecular weight polyethylene, which are all possible materials for making spacesuits or lunar-based material. We will be testing which material is the most effective at long-term resilience to lunar regolith. Our hypothesis is, if all materials are exposed to lunar regolith, Kevlar 29 will be the most resilient. We believe this is so due to its thermal properties, high strength, and resistance to tear. In this experiment, we set up 2 rows of the same materials, one row using an electrodynamic dust shield and the other being a control group. These patches will be on the outside of our lunar base, exposing them to lunar regolith.
Another addition to this experiment is testing electrodynamic dust shield with the hypothesis of if we use EDS on materials once a day, the long-term impacts on the materials will decrease. EDS, as Judith explained, uses transparent electrodes and electric fields to lift and remove dust from surfaces by oscillating electric fields across the fabric. Our test will compare each material in the control group again by using EDS daily to remove the regolith. We will measure the efficiency by weight and visual observations. This aims to test the effectiveness of EDS in the long-term scope. This will also have implications for both spacesuit materials and lunar base materials with both short-term and long-term durations.
Progressing lunar agriculture with native thalecrest or plant aims to test the feasibility and differences of growth of Arabidopsis thaliana in the lunar environment. The goal of the experiment is to determine if there's a benefit in growing Earth-native seeds in lower gravity conditions and analyze if thalecrest can survive in lunar conditions as opposed to just lunar regolith. Our null hypothesis is that thalecrest's growth on the moon will be slightly worse with artificial lighting and much worse in a greenhouse with natural light compared to Earth conditions. However, if the null hypothesis is rejected due to significant evidence, it could mean that plants are just as, if not more, viable to be grown on the moon compared to the Earth.
We'll plant 30 samples of thalecrest in each of the 3 environments tested. The thalecrest used in the experiment is ecotype Columbia 0, which was previously successfully grown in the lunar regolith on Earth by Dr. Furrow and Dr. Paul. Data will be collected by measuring plant height and biomass. Additionally, the thalecrest's growth rate will be monitored and compared across tests. All seeds will be planted in lunar simulant JSC-1A. One group will be grown on the Earth, and 2 other groups will be grown on the Moon. The group planted in artificial light on the Moon and the Earth will receive UVA lighting. The group exposed to natural light will be planted in a greenhouse. Inserting perlite and sticks into the lunar regolith will make the soil more porous, allowing water to reach the roots of the thalecrest.
We are designing an experiment based on the extraction of oxygen from lunar regolith from different depths of permanently shattered regions, or PSRs, on the lunar surface.
While speaking with subject matter expert Miss Anastasia Ford, we began thinking about applying the principles of our oxygen extraction lab to our mission to apply on the lunar surface.
Lunar regolith contains about 40% oxygen, along with various other metals and carbons. Inspired by this composition and Miss Ford's research, we developed our own oxygen extraction experiments.
This is a landing site that we will be conducting our experiment from. To diversify our data, we will collect regolith from 2 different depths of the moon, allowing us to account for discrepancies in their conditions they have always been subject to. The regolith collected for our test will be conducted by using a rover or spacesuit EVA to access the 2 depths. Using the NASA-proposed Lunar Terrain Vehicle and a drill, we will be collecting samples of 100 grams of lunar regolith from different depths in the lunar highlands.
At a big picture, our experiment will test the oxygen levels in lunar regolith by subjecting it both to carbothermal and catalytic reactions to produce oxygen gas. Here is a diagram of all our experimental features and variables.
We'll collect all samples from the same area to avoid bias. For each depth, we'll gather 8 separate samples to account for regolith variability.
Here are the steps to our experiment in 5 simple steps. The screen shows the carbothermal reaction of the card reactor. A laser melts the regolith and methane is added, releasing oxides trapped in metals, most primarily silicon oxide. This process releases hydrogen and carbon monoxide. In the catalytic reactor, hydrogen and carbon monoxide combine to produce water and methane. Methane is recycled for further reactions, or it could also be used as propellant, while water undergoes electrolysis to separate oxygen and hydrogen, completing the lunar regolith oxygen extraction process.
The extraction of oxygen from lunar regolith is crucial for a long-term moon base, reducing the need to bring oxygen from Earth. This saves storage and avoids technical issues. Additionally, the oxygen can help manufacture water and fuel for extended lunar missions.
An essential part of our lunar mission is quickly transmitting data back to Earth. This enables NASA scientists to analyze it in real time, maximizing efforts during and after spacesuit EVAs. Our experiments generate vast data, including oxygen levels, atmospheric pressure, temperature, and other variables, all of which must be relayed back to Earth. The most innovative data transfer method for our base is the LINE, which stands for the Lunar Infrastructure Optical Node made by FiberTech. This is a laser-based transmitter proposed in DARPA's 10-year lunar economy plan. LINE uses laser transmission to connect with Earth or other orbiters, seeking contact points to send data quickly. NASA's Lunar Laser Communication Demonstration has shown that this can achieve download speeds of up to 622 megabits per second. LINE will enable communication with Earth and across the lunar surface, supporting astronauts on EVAs or rovers. Data from our experiment and lunar-based vitals will be stored on solid-state hard drives with space-hardened RAM. LINE will transmit this data back to Earth. With powerful laser transmitters, I estimate data transmission latency from the lunar surface to take about 5 to 8 seconds. To ensure stable data transfer, the node will connect to the gateway station, which will then relay it to the TDRS satellites orbiting Earth. These geosynchronous satellites handle most of NASA's data relay and will send the information to JSC or any other NASA facilities for analysis.
Our experiments will try to be processed and recorded on the lunar surface or gateway in order to avoid any accidents during transport or unnecessary handling. If necessary for our experiments or samples to be brought back to Earth, careful monitoring of safety, temperature, pressure, radiation, and more will be practiced. After 45 days, the astronauts will begin their safe journey back home through the lunar lander in the help of Gateway. This approximately 3-day journey will demonstrate the capabilities of spaceflight and our hopes to explore human curiosity for the betterment of humanity.
In reflection, we have all grown so much through this internship and have learned so much more about STEM paths, as well as just so much about ourselves, having the opportunity to interact with like-minded peers, as well as just grow within our knowledge of what we want to pursue in the STEM field. And this has happened because of the speakers we've had an opportunity to meet with, as well as the Z-Cube experiment, as well as our individual project. All of these things have helped form our team and each of us individually to the next level. And I think we would all agree that this internship was very changing and very helpful in our STEM careers and our STEM knowledge. And we would like to thank our mentor, Dr. Lewis, as well as Miss Busby, for creating this opportunity and allow us to grow in these ways, as well as just all the C staffs, as well as just highlight some of our favorite things we've done. We had a mentor dinner, we've met on Zooms, we went to JSC, we had a barbecue cookout, we did experiments with petri dishes, we did iFly, we went to Fiesta, Texas, and that's just another photo from iFly. And then lastly, these are all the sources we've used.